So yesterday we looked at electromechanical system, the modeling of an electromechanical system. We wrote the equations for that, and then I told you that once you have a mathematical model for a system, to analyze it, what you need to do is to solve for those equations. Okay, and solving for these equations is in general not an easy task, and the analytical solution is possible only for under certain conditions, and you cannot guarantee that you can find an exact analytical solution for all problems. In fact, when you want to find the forced response, the solution depends on the input you have, and unless the input is a well-defined function like a sine wave or a step function, you cannot define an analytical solution. If the input is an arbitrarily changing signal, something like this, so you cannot find an analytical solution corresponding to the system response for that input. And even for the cases where analytical solution is possible, it is not easy, right? So to solve the linear ordinary differential equations for such systems, we use Laplace transformation. So I understand that you have seen Laplace transformation before, so you know what it is and how it is used. So we're going to do that, but let's start with a review. So some of this material will be a review for you. If you look at these lecture notes, there's a heading complex variables, but this part is not complete. So I'm going to give you this other file, which includes a complete review of complex variables and Laplace transformation. So this is another file, so I'm going to post you this as well. So let's take a look at this quickly. Okay, so the Laplace transformation involves complex variables. Okay, so before talking about Laplace transformation, let's remember what a complex number is. Let's start from there. So as you know, a complex number has two components. It has a real component and an imaginary component, and the J here represents the imaginary part, and it is, as you know, the square root of -1. So different from a real valued number, a complex number has two components, and you can represent a complex number on a complex plane. In fact, we use this complex plane representation a lot. So in a complex plane, the horizontal axis is chosen as the real axis, and the vertical axis is the imaginary axis. And if you have a complex number like 3 plus 5i or 5j, then you can show it on a complex plane by marking the real and imaginary component. And on the complex plane, sometimes most of the time we use Cartesian coordinates. That means we use the real axis component and the imaginary axis component. But you can also use polar coordinates, right? And in polar coordinates, you express the length of the number, which is the distance from the origin to the complex number, and then the angle it makes with the real positive axis. So this is the length and this is the angle. Okay. Next, let's talk about complex functions. A complex function is really not different from a regular function. So it is a function of a variable. So you present it in this form. The variable in the parentheses is the argument of your function. And if the function can accept complex numbers as arguments, then we call that function a complex function. So for example, if you have a function like this, s squared plus 2s plus 1, for example. So this is a polynomial function in S. So if S is a real number, then it's a real valued function. But if S can be a complex number, then this becomes a complex function. And if S is a complex number, then in general, the value of the function will also be a complex number. For example, if S is 1 plus I, for example, then the value of the function for that S will be, so let me just use MATLAB to find that number. So let me call this S is equal to 1 plus I. and then g is s squared plus 2s plus 2, I think, was it? No, plus 1. Let me make it 2. So the value of the function is 4 plus 4i. Or if the s was minus 1 plus I, for example, let me change the value of the s to minus 1 plus I. The value of the function for that case is 0. I mean, it doesn't have to be a complex number. The value of the function can be real or complex. Okay, let's see what else we have. Okay, so we have this example where this time we have a rational function. G of s is defined as you see here. And if you insert a complex number, like sigma 1 plus j times omega 1, so what I'm showing here is that the value of this function is a complex number. Even though this is a rational function, if you put this complex variable into this function, and if you do the simplification, so you have s here and then s plus 1 here. So when you have such complex numbers in the denominator, you can get rid of them by multiplying both sides of your ratio with the complex conjugate of that number, right? So hopefully you remember that trick. So the complex conjugate of a complex number is the same number with the imaginary part being negative of the original number. So maybe I can carry this over to the and in general, the complex conjugate is represented by a bar over the variable. So S1 bar is the complex conjugate. This is going to be sigma 1 minus j omega 1. So what I do here is, so this is my original function. I multiply both sides of this ratio with the complex conjugate of this thing. And then I do the same thing for the complex conjugate of the other thing. And in the end, on the denominator, you're left with a real number, because whenever you multiply a complex number with its complex conjugate, you get a real number, right? So let me just say that always real. So that means in the end, on the denominator, you're left with a real number, and you have complex number on the upper side. In the end, the value of your function becomes a complex number. So this is the real part, this is the imaginary part, and it can be written as so it basically, this general form is still valid. Okay, a real part and then imaginary part. Okay, so as I told you that we use imaginary plane a lot to represent these numbers. So any complex number can be shown with a point on the complex plane, and if you feed this complex number into a function, then the value will in general be a complex number, and then the value of the function can also be represented on another complex plane. So this is what we see here. So this is for the same function. So we're still talking about this function. So this is our function 1 over s times s plus 1. If you feed this number into this function, the output of the function is this point. Okay, so this function maps every point on the left plane to another point on the right plane. Okay, so let me do some tricks. Since we have some additional time, let's use that time to use MATLAB to show these mappings. Okay, so we know that, in fact, let me just show that in MATLAB. So my original point is 1 plus j, and then I feed it to this function. So let me calculate the value of that, 1 over s times s plus 1. See, this is the value of the function. This is what we found, as you see. So let me see what the value of this point is, and that point is, and that point is. So in other words, let me just find where this straight line that I draw here maps to on the right plane. Okay, so let me just try this. So let me choose an interval. So let this run from -2 to +2, and let me find the mapping of this straight line on this function. So I was writing a code for that. So let's see. So the real part goes from -2 to +2. So this is that vector with this increment, and my s function variable also has an imaginary part, a constant imaginary part of j. So let me define s as g plus j. Okay, and let me calculate the value of the function for that s vector. And then once I have this, f now contains a vector of numbers that correspond to the values of correspond to this line. So let me just run that. Okay, so now f is a complex number, and obviously this was not correct. So, and MATLAB is warning me that the imaginary parts are now ignored. Obviously, that's not what I wanted to do. I wanted to plot the real value, the complex numbers on the complex plane. Right? So here's how I should have done that. So I should have done plot. The horizontal axis should be the real values. So I can write that real f. So I know that f is a vector of complex numbers. So on the horizontal axis, there should be the real values of that vector. And on the vertical axis, there should be the imaginary values, or the imaginary components. Okay, so this is where it maps to. So let me okay, so I just scaled the graph such that the aspect ratio for this screen is 1. That means, so this part has 1.4 units, and this has the same scale. So anyway, what this So this shows that this line here maps to this blue curve. Okay. Good. Oh, by the way, this mapping is not one-to-one. That's what this sentence says. GS is a single-valued function since it maps any point on the left plane to a single point on the right plane, but reverse is not true. So you cannot say that any point on this will map to one point here. So it's not a one-to-one mapping. Okay, now let's define an analytic function. A complex function is said to be analytic if that the value of the function and all its derivatives exist. So this means the value of the function and the derivatives of the function everywhere should have a finite value. That's what we mean by derivative exists. So if the derivative or the value of the function becomes infinity, then that means that function is not analytic. So let's take a look at this example. So this is an analytic function because the value of the function is finite for every finite s number. Or if you take the derivatives, the first derivative is going to be 1, and all the higher derivatives will be 0. So so none of these values will become infinity as long as S is a finite number itself. So this is the analytic function everywhere in the finite S-plane. But if you look at this function, so this is the function we used before, there are some points where the value of the function doesn't exist, right? And in fact, the point for which the denominator becomes 0 makes the value of the function go to infinity. Okay, so and there are two such points. The first point is S is equal to 0, so this is a real number. And if you feed this real number into this function, you will get infinity. Or there's another one, which is S is equal to -1. If you feed this number into the function, you will also get an infinity. Okay, and those 2 points are, the first one is S is equal to 0, the second one is S is equal to -1. So let me mark these points here. The first one is S is equal to 0. It's a real number, no imaginary part. The second one is S is equal to -1. So these 2 points have no finite value on the right half plane. Okay? Efendim? Doğru, eksi olduğuna göre sol olacak değil mi? Yeah, it's absolutely true. This is -1, so let me just carry it over here. So these 2 points have no corresponding mapping on the other plane. So, and let's in fact try that. So I know that this line maps to this blue curve here, and let me just shift this line down and see where it maps to on the right half on the other plane. Okay. So all I need to do is I need to go back to this MATLAB code, and here I defined this real valued vector, and I added a constant complex component of J. So all I need to do is I need to just remove this part. So let me just remove this part, and if I do that, my S vector becomes this real valued vector, which corresponds to this line here. And let me just run the code one more time, and let me hold the graph so that I can plot it on top of this figure. And let me use red color so I can distinguish them. Okay, this doesn't look good. So let me just make this data aspect ratio. Let me just remove that. Okay, still not very nice. So anyway, if you look at this function, and if you consider the definition of an analytic function, where this is a complete analytic function in the finite S-plane, the other one is not. There are 2 points on the finite S-plane where this function is not analytic. Okay? Now, let's define the singular points of a complex function. So points in the S-plane at which the function is not analytic are called singular points, and they are also called poles. At poles, g of s or its derivatives approach infinity. If you go back to the same function, this function has 2 poles. Okay, so one of them is at s is equal to -1, the other one is at s is equal to 0. And for these 2 values, the value of the function doesn't exist. So these are the 2 singular points for that function. So once you define a pole, then you can talk about multiple poles. And a pole on the S-plane is said to have multiplicity R if these are valid. So let's see what this says. So the SI is your pole. Okay, so you multiply your function. So first of all, we know that g of s doesn't have a finite value at this point, right? since it is a pole. But if you multiply it with s minus si and the value becomes a finite number, then that means you have a single pole. But if you have to multiply it by s minus si to the power r, and r is a number greater than 1, that means you have a multiple pole there. So we should just talk on some examples. So if your g function is something like s plus 1 over s times let me make it as plus 2. So we have two poles, one at 0 and one at minus 2. And for the pole at s is equal to 0, the value of the function times the value of the function is infinity, but the value of the function times s is 1 over 2, right? And it is not infinity. So that means r is 1 for that pole. So so this is a single pole. It doesn't have any multiplicity. But if this was something like s to the power But if that was something like s to the power 3, then the value of the function at 0 is infinity. The value of the function times s is still infinity, right? So if you multiply this with s, and you still get two s's on the denominator, and the value of the function times s squared is still infinity. And finally, the value of the function times s to the power 3 becomes non-infinity or finite. So this means r is equal to 3. Okay? It's just so for that power there determines the multiplicity of the pole. And s is equal to minus 2 is a pole with r is equal to 1, since there is no power term here. And there are these examples. So if you look at this thing here, so you can immediately tell. We don't really need to check this, obviously, because it's really obvious here. So you have one pole, and there's no power here. So this is a simple pole. You have another pole at minus 1, which is also a simple pole. And then you have another pole at minus 3, but this has a multiplicity 2, since you have 2 on the power. Okay, so these are the poles of a complex function. And similarly, you can talk about the zeros of a function. So remember, the single points or the poles were defined as the points on the S-plane at which the function is not analytic. And you define the zeros as the points on the complex plane at which the function has a value of 0. Okay? So if you consider this function, for example, this has a 0 at minus 2, right? Because at s is equal to minus 2, the value of the function becomes 0. And you define multiplicity in exactly the same way. So this has a 0 at minus 2 with multiplicity 1. If there was a power here, a power n, for example, then that 0 would have multiplicity n. Okay, so this is all the information we really need to define Laplace transformation. But before that, I should have defined rational functions, but I cannot really see it here. But I think I saw it here on the other notes. So this is really important since we will be using pretty much rational functions all the time. A rational function can be defined as follows. It's a function which can be written as ratio of two polynomial functions. You know what a polynomial is, right? So a polynomial function is a function that contains the argument and its powers with some constant coefficients. Okay, so if it's a polynomial of s, on the right hand side, if you have powers of s with some constant coefficients like this, then that becomes a polynomial function. So, for example, a function y of s in general, if it has this form s to the power n plus a n minus 1 s to the power n minus 1, and it goes all the way up to a constant term of a0. So this is a polynomial of order n if an is not equal to 0. Okay, so if the highest order here is n, then that's an nth order polynomial. If you have two such polynomial functions, and if you divide them together, that resulting function is called the rational function. So for example, like this one, this is the first order polynomial, it's a second order polynomial, and the ratio of the two gives you a rational number. In fact, all the examples we saw before were rational functions, right? So this is a rational function, this is a rational function, they are all polynomial functions. Okay, so remembering these things about complex variables and complex functions, we can start talking about Laplace transformation. Many common functions like step function, sinusoidal function, exponential function of a real valued variable can be transformed into algebraic functions of complex variable s. The new function still represents the same original function, but expressed in a different mathematical space or different mathematical form. Well, this is actually my analogy. So this is in a way similar to explaining the same thing in a different language. It may not be a very good example, but I think it gives the idea. So you have a function of variable time, for example. When you take the Laplace transform of that function turns into a different shape. It becomes a different function, but it becomes a function in a different domain. And the reason why we do that is many complex terms turn into much simpler forms. For example, like this. And the biggest benefit is when you consider differential equations, right? So the differential equations, when taken the Laplace transformation, turn into algebraic functions, and that's what makes this so powerful when solving for differential equations. So this Laplace transformation is, I think, in a way similar to using different languages. Okay, so I'm trying to explain these things in English, and I can say the same things in Turkish. So you will hear different sounds, but essentially I'm trying to say the same thing. So you have expressing the same thing using two different languages. And so this language example is not very good in the sense that you don't get such a huge benefit by using a different language. So anyway, but in the case of a Laplace transformation, you get huge benefits if you are dealing with differential equations. Okay, so the differentiation integration can be replaced by algebraic operations in the complex plane. Okay, so let's remember how the Laplace transformation of a function can be taken. So this is your original function represented in time domain. So you have any function of time. So this is how the Laplace transformation is taken. You take that function and you put it in this into this function. So this is your original function. You take that function, multiply that with this term, e to the power minus st, where s is a complex variable, and you take the integral of this function from 0 to infinity. So this is one-sided Laplace transformation. So in the original function you have t, right? And then you also have t in this exponential term. But when you take the integral, the time dependence disappears, right? When you take the integral in a certain interval, in this case the interval is from 0 to infinity, in the end the time dependence disappears and you're left with something that is a function of s only. So this little s becomes the only variable in the function. And there's a little detail here. It says, provided that there exists a real positive sigma such that this integral has a finite value. Okay, so you don't really worry about these details too much, because we will not be using this integral. We don't use this integral at all. We don't take the Laplace transformation of different functions manually. Instead, we use Laplace transformation tables. We only consider some known generic functions for which Laplace transformation is available. Okay, so let's take a look at some examples though. So even though we will not be taking this integral in our daily lives, let's take a look at how that integral is taken and how the Laplace transformation of some basic generic functions are obtained. Let's start with the unit step function. The unit step function is this function. We have seen this function several times before already. So it's a function that is defined in a piecewise form. So the value of the function for negative t values is 0, but for all positive t values it has a value of 1 if it is a unit step function. So since we call it unit, the value is considered as 1. Since you are taking the integral from 0 to infinity, so we're taking the integral we will be taking the integral from 0 to infinity, right? So we are considering this right half part. So we don't care what the value of the function on the left hand side, since we start the integration from 0, as you see here. So the value of the function in this positive time range is 1. So this is our function. And we multiply that with e to the power minus st. And then perform the integration. The integral is taken as follows. The integral of e to the power minus st is the same thing. We just bring minus 1 over s as a multiplicative term. And now we take integration between these limits from 0 to infinity. So the value of this thing at infinity is 0, since you have e to the power infinite on the denominator, minus you evaluate this function at t is equal to 0, and for that you have 1, and in the end the integral gives you 1 over s. Okay, so if you take the Laplace transform of the unit step function, you get 1 over s. That's the end result. Next we take the Laplace transform of this function, e to the power minus at. and the result is shown here. For the unit step function, we had 1 here, but when taking the Laplace transform of this function, you put this term, e to the power minus at there. And if you take the integral, it turns out that the value of the Laplace transform is 1 over s plus a. Okay, so you already see here that the Laplace transformation is a good thing, that it turns complex function into simpler forms, right? So the Laplace transform of unit step function is 1 over s, but the Laplace transform of this function, e to the power minus at, is 1 over s plus a, right? So you get rid of this exponential term, and instead you just get this in the denominator. Okay? So you have seen all this before, right? So did you? Şu grafiği mi diyorsun? Bu şey orijinal fonksiyonun grafiği. Ya bu UT'nin bu şeyde. So this is the graph of unit step function. This is the original function, not the transformed function. The transformation of that function is 1 over s. Okay, so let me just stop here and we will continue next week.